Okay, let's do one more two-dimensional kinematics example, and then we'll go on to the next topic. Uh, so let's figure out what happens. So say you're driving a car, let's say uh, 30 meters per second, driving a car 30 meters per second, and you throw a ball up in the cab of the car. Okay, what what happens, like in your experience in the car, what happens if you throw something up in the air? Where does it land? It lands back in your hand if you throw it straight up, right? So I think that can be sort of how that works can be sort of a confusing thing to people. So let's do like an analysis of what happens when somebody's driving in a car 30 meters per second, throws something up in the air. We know it's going to land back in their hand. How does that all work? Like, how does everything go together to make that happen? Um, so um, a car is driving 30 meters per second. And a passenger throws a ball straight up. Um, so first, uh, and let's say that, I guess we have to give it an initial velocity. Let's say that um, so let's say that it has um, upward velocity of 3 meters per second. So first, how far has the car traveled when the ball returns to the person's hand? And what does an observer see, an observer outside the car see? Okay, so um, the car is going this way at 30 meters per second. Um, and at this instant, the ball's thrown up into the air. Um, and then the car, it's going to take some amount of time for the ball to come back to the height of the hand. So at this point, it returns to the hand. And we want to figure out what this distance is. All right, so the first thing that, so let's just go through the steps of the 2D kinematics problem. So we need to figure out, we need to choose a time equals 0, an instant for time final, an origin location, and a coordinate system orientation. Time equals 0 is going to be the instant that the ball's thrown. Time final is going to be when the ball returns to its starting height. The origin we're going to put on the ground right beneath where the ball is at time equals 0. And the y-axis is going to be up. The x-axis is going to be horizontal in the direction of motion. So those are shown in the picture. And now we can think about what we know and what we want. Okay, do we know the amount of time it's going to take for the ball to return to its starting height? No. Do we know the initial position? Not really. Well, why what? The origin. You could do it either way. I think the way I usually do it is put the origin on the ground, so we can do it that way. Do we know the initial position, the position at time equals 0? Well, so first of all, we know that the x position is 0, so pix is equal to 0. And then piy, do we know that? Well, it would have made it a little simpler if I would have put the origin at the hand, because then we would know it was 0. But let's say we don't know what it is. We don't know what that height is. So we're just going to call it piy. Okay, so do we know anything about the final position? Pfx is what we're trying to find. Pfy is piy. So I'll just write it like that. Do we know anything about the initial velocity? Okay, so yeah, so Vix, horizontal velocity of the ball. The hand is just throwing it straight up in the air, but the hand's doing that while it's moving horizontally at 30 meters per second. So Vix is positive 30 meters per second. And then Viy is the upward velocity of 3 meters per second. And then we don't know anything about the final velocity. Is there an equation that we can use for this? Yeah, but we don't want to write that down, because if we do, it's going to look like some equations will work that aren't going to work. So we'll just say we don't know anything about the final velocity. Okay, so is there an equation that works with this? No. Oh, and we know the acceleration. Sorry. Move this. It's in free fall, so ax is 0, ay is negative 9.81. Okay, but no equation works. So what do you want to try as an intermediate variable? Yeah, time final. So we'll hold off on trying to find p of x, and we'll try to find time final. So is there an equation that has time final in it and everything else is known? The one that should work is p f y is equal to p I y plus v I y t f plus 1/2 a y t f squared. And so to fill this in, I'm going to replace pfy with piy. We know that that relationship holds. Okay, everyone with me on that? So what we're saying is we know that those are the same thing. So we have piy is equal to, this is still piy, plus 3 tf plus 1/2 times negative 9.81 tf squared. Now we can subtract piy from both sides. This is just a variable. So those two cancel out. And we get 0 is equal to negative 4.905. I just rearranged these two terms. Tf squared plus 3tf. How do you solve that equation for tf? Quadratic formula will work. Or if you see it, you can factor out a tf. Each of these two terms has a tf. So you get tf, no, tf times negative 4.905 tf plus 3. And so what values of tf make this, the stuff on the right, equal to 0? So we have two things multiplied together, this and all of this. The only way for all of it to be equal to 0 or for one of these two terms to be 0. So one solution is tf equals 0. That'll do it. That's not the one we want, but that's a root. And then the other one is if the stuff in parentheses is equal to 0. So that requires that TF is equal to 3 over 4.905. Can someone tell me what that is? So set this equal to 0, set the stuff in parentheses equal to 0, 0.611 seconds. And that's what you would get from the quadratic formula too. Okay, so now usually when we have two values of time, one's negative and one's positive, and that's how we know we only want the positive one. These are both possible times, right? Neither one of them is negative. How do we know which one of these we want? We don't want 0 because, so what we're saying is, how long does it take for the object to get to the height that it starts at? 0 is saying, well, it's at the height it starts at right when you throw it. So that's the one that we don't want. What we do want is the other one. So it's going to take 0.611 seconds for it to get back to the hand. And now that we know that, we can think about what we know and what we want again. We know the acceleration. Now we know time final. We know the initial x position is 0. We don't know the initial y position. We want to find the final x position. We know the final y position is the initial x position, is the initial y position. And we know the initial velocity, Vix is 30 and Viy is 3. Okay, so is there an equation that works with this? I think the one that should work is Pfx is equal to Pix plus Vix Tf plus 1/2 Ax Tf squared. So Pfx is equal to 0 plus 30 times 0.611 plus 1/2 times, what's the x component of acceleration? 0, so this term all goes away. And so we get that Pfx is equal to, what's that? 8. Can someone multiply 30 and 0.611? 18.33 meters. Okay, so when you throw an object up in the cab of a car, to you, you're in the car, it just goes straight up and comes straight back down. But to somebody on the street who watches this happening, what's going on is so your initial velocity vector has an x component of 30 meters per second and a y component of 3 meters per second. So this is your initial velocity vector. And so it looks to somebody on the street like the object that you throw is being thrown out almost horizontally, barely up at all, almost like this. And it follows a path like this. When it gets back to that starting height, it's traveled a distance of 18.33 meters. Anybody have a question about that? Is that something you've wondered about before? Like what happens? I don't know, maybe not. I used to wonder about that. So it's exactly the same as like if you took the keys or the ball or whatever you throw in the cab, it's going to follow the exact same path as if you just used a pitching machine or something and pitch something out with a velocity vector that had an x component of 30 and a y component of 3. Follows that exact same parabolic path. It's just to you because you're traveling sort of along with it, it looks like the thing just goes straight up and straight down. Has anybody done the helicopter problem in the practice problems yet? Did you get stuck at all on it? Was it confusing? Let's, okay. Let me do an example that's sort of like that one. Uh, what number is it? Do you remember? Okay. Oh, so the observer sees this thing. Uh, the observer sees what looks like the object. So the car is moving around the thing, but if the observer ignores the fact that there's a car there, it looks like this object is launched out with a velocity vector that's equal to 30 in the x, 3 in the y, and it follows a shallow parabolic path, and in 0.611 seconds, it travels a horizontal distance of 18.33 meters. Okay, so this is like number 2 in the practice problems. Let's say that we have a helicopter that's traveling 20 meters per second. At an angle 5 degrees below the horizontal. And when the helicopter is at a height of 30 meters, an object is dropped. So first, how far away is the object horizontally when it hits the ground? Okay, so in the time between when this object is dropped and when it hits the ground, how far has it traveled horizontally? And then second, how much lower is the helicopter when the object hits the ground? And we're going to assume that the helicopter keeps moving with the same velocity, stays on the same line it was on, and the speed doesn't change the whole time that the object is falling. Okay. Okay, so let me draw a picture of what's happening. So here's the helicopter. I just like to do problems with helicopters because I know how to draw them. So there's the helicopter. And if this is horizontal, the helicopter's moving at an angle of 5 degrees below the horizontal. And at the instant this object's dropped, the height of the helicopter is 30 meters. And then this object is dropped out the window. Before we start doing calculations, so I think something that's sort of natural for a lot of people to think is like, okay, so you just hold this thing out the window, the helicopter is cruising along, you let go of it, and the object's just going to come straight down as the helicopter goes this way. But that's not what's going to happen. What's the rule about the velocity at the instant something's dropped? You remember we talked about? Yeah, it's this. So at the instant it's dropped, the velocity is the same as whatever the velocity is of the thing it's dropped from, the velocity of the vehicle. So if it's dropped from a helicopter that's going 20 meters per second that way, it's just like this being at rest and being launched out at 20 meters per second, 5 degrees below horizontal. So this object is going to start out at that angle and then fall down to the ground like this. And so it's going to hit the ground somewhere over here. And so this path is going to look something like that, part of a parabola. And we want to calculate this distance. Okay, so to do this calculation, we first have to choose time equals 0, time final, the origin location, and the coordinate system orientation. Like I always do, I'm going to put the origin on the ground right below the object at time equals 0. Time equals 0 is going to be when it's dropped. Okay, so time equals 0 is when it's dropped. Time final is when it hits the ground. The origin location is on the ground. The y-axis is up, like shown. And now we can think about what we know, what we want to calculate. Okay, do we know time final? Nope. Do we know acceleration? We're doing the calculation for the object that's dropped. We're going to assume that's in free fall. So the x component of acceleration is 0. The y component is negative 9.81. Do we know the initial position? We do. What's the x component? Yep, 0. What's the y component? Yep, positive 30. Do we know the final position? For y, we do. For x, we don't. That's what we're trying to find. PFX is what we're looking for. But PFY, we know it's going to end up on the ground, so 0. And then the last thing is, do we know the velocity vector, the initial velocity vector? Yeah, you know because I'm writing it. That way of knowing doesn't work on a test, though. Okay, so how do we fill these in? Yeah, so we know that if this is the coordinate system, This vector is 20 meters per second long, and this angle is 5 degrees. So that initial velocity vector is 20 times the cosine of some angle, 20 times the sine of some angle. And that angle is the counterclockwise angle from the x-axis. Or you can call it a negative angle and go clockwise. So what angle do we want to use here? Yeah, 355 works, or -5 works. Can someone calculate? Okay. 7.4. Okay. So the x component is 19.92, and the y component is -1.74. And then we don't know anything about the final velocity. Okay, so is there an equation that has p of x and everything else is known? No. So what should we try to find? What? Time final, yes. All right, so is there an equation that has t final in it and everything else is known? I think the one that works is pfy is equal to piy plus viy tf plus 1/2 ay tf squared. So 0 is equal to 30 plus -1.74 tf minus 4.905. That's 1/2 times -9.81 tf squared. And how do we solve this for tf? Yep. So there's A, there's B, there's C. Can someone who has that program in their calculator punch that in? $2.302. Yeah, was there another one? Oh, negative something. Okay, that's good enough. Okay, we don't want the negative. We want the positive. So now we also know the time. And now we can go back. Is there an equation that has P, F, X? And now we know time final. We know the acceleration, all the things we knew before, plus TF. And so I think the equation that we're going to use here is PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 19.92 TF plus, what's AX? 0, so that term goes away. Oh, and I didn't put in the TF, we know. 2.30. And so PFX is equal to, what's 19.92 times 2.3? 45.8 what? Meters. Okay, so this object travels horizontally 45.85 meters. Okay, that part of the problem was just like the car problem. But now the next part is the part that's a little tricky, or you just have to be aware of the difference for this part. So part B, we want to know, so the helicopter is headed sort of down, a little bit down, and it takes 2.3 seconds for the object to hit the ground. So the helicopter in that time, goes down a little bit, right? So now we want to calculate in those 2.30 seconds, how much lower is the helicopter than it was before. So how much lower is the helicopter after 2.30 seconds? Okay, well, for the time equals 0, the time final, the origin location, and the coordinate system, we can just keep all this stuff the same. There's no reason we have to change any of that. And so now we can think about what we know, what we want. Okay, so we know time final, right? Because it's asking what's happening in the time that it takes for the object to hit the ground. So time final is equal to 2.30 seconds. Now, what about the acceleration? This is the part that's easy to mess up in this problem. What do we know about the acceleration? So first, problems that we do are mostly free fall problems, but helicopters, a well-designed helicopter is not in free fall, Um, the whole idea of it is that you get enough interaction with the air that you can hold whatever kind of motion you want. So the velocity in this helicopter is constant. And what's a synonym for a constant velocity? Zero acceleration. Acceleration is a measure of how much the velocity is changing. So for the helicopter, AX is equal to 0 and AY is equal to 0. What would you get if you said that AX was equal to 0 and AY was equal to negative 9.81, like in free fall? How much lower would that say the helicopter was in 2.3 seconds? 30 meters, because if both of these things were in free fall, the helicopter and the object would just hit the ground at the same instant. Okay, what the initial position of the helicopter is the same as the object, so 0, 30. The final position, yeah, we want to find the final y in this case. We want to find out how much lower it is. Um, and then the velocity, the initial velocity, is the same as for the object. So that's 19.92 for the x component and negative 1.74 for the y component. And we'll say that we don't know the final velocity, even though it's a constant velocity, so that's going to be the same final. Just filling that out in this case would make it look like equations work that didn't. Okay, so is there an equation that works to find PFY with these knowns? I think this one should. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So PFY is equal to 30 plus negative 1.74 times 2.30 plus AY for the helicopter is 0, so that term all goes away. And so can someone calculate PFY? $25.994? 25 point, I'll just call it 99. Now, we wanted to know how much lower it is. So how do we use this number to calculate how much lower it is? Just subtract. What we're really doing is calculating the y component of the displacement. So the y component of the displacement is the later position minus the earlier. And so you get negative 4.01 meters. So in that time, the helicopter has gone 4.01 meters lower. Any questions about that? Okay. So that's all for 2D kinematics. And so now we're finally getting out of kinematics. So remember what kinematics means? That's right. So until now, we've been talking about describing the motion without knowing anything about the cause. Sort of a gray area is talking about free fall, where we sort of like implicitly included the force of gravity in there, but we didn't talk about it yet as a force. But so now we're going to go on to the next topic where we do talk about the causes. So we're going on to 2D kinetics. And kinetics combines kinematics with causes of motion. And that's going to require us to talk about two new quantities. And those are mass and force. And so I'm going to start by defining mass. That's going to be the simpler one to define. That'll be fast. And then for a long time after that, we're just going to talk about defining different types of forces. So the first one, the easy one, is mass. And what mass is a measure of an object's resistance to acceleration. How hard is it to accelerate an object? So, for example, if this football player collides with this football player, um, what's going to happen is when they collide, this guy is going to experience a big acceleration. This guy is going to experience a very small acceleration. You won't even know that this has happened. You know, that's why in the positions where all you're trying to do, like on the offensive line, all you're trying to do is accelerate people backwards. That's your only job. You never see in the NFL people who look like that. So when these two players collide, the big guy won't accelerate much. And that's because he has a lot of mass. and therefore he's more resistant to acceleration. The little guy will accelerate a lot. Um, because he has a lot less mass. Um, so you think of mass and weight as being sort of synonyms of each other. Uh, your like a bathroom scale has uh, usually you can switch on the bottom from pounds to kilograms, whatever you want to measure in. Well, pounds is actually a measure of force. That's a measure of how hard gravity is pulling on you. That's a force. Um, Kilograms is a measure of mass, and that's not really a measure of how hard gravity is pulling on you. Um, they do relate to each other, and we'll talk about that, but the scale isn't really directly measuring your mass. A scale is just measuring how hard your foot, how much force your foot is pushing into the scale. And scales like that, so that works fine, with a scale, with a conversion factor, you can use a bathroom scale to measure how much mass you have as long as you know what the acceleration of gravity is. But like for astronauts who are in orbit, you can't use a bathroom scale because there's no apparent gravity. Like if you're in a place with no gravity, people are just floating around in this ship, whatever. Um, they don't put any force on a scale. Like they'd have to hold themselves down onto the scale to stand on it. So like the idea of measuring mass with a bathroom scale, it's meaningless. There's no way to do it. And so, but it's actually for astronauts, it's really important to be able to accurately measure their mass because it's really easy to lose a lot of bone density, and that's really dangerous. And so they're really careful every day about measuring their mass, making sure they're not losing too much weight. The way they do it is they have a contraption that I've never seen, but I imagine it's like in the old J.C. Penney catalogs in the exercise section. There used to be these things that would like jiggle you. Anyone remember those things, or like in old cartoons? But it like jiggles their body. It applies known forces to them and measures how hard it is to accelerate them. And based on how easy or hard it is to accelerate, they get a measure of the mass. Because what mass is a measure of how hard or easy it is to accelerate. Um, the SI units for mass are kilograms. And one thing to notice about mass is um, mass is a positive number. Um, and so that means it's not directional. Uh, so we're not going to be treating mass as a vector. Uh, a single thing is just associated with a single positive number. And what that means too, this is going to be important, is if you multiply a vector quantity, any vector quantity, to the mass, in our case, the one that's going to be important is the vector acceleration. So if you multiply an object's mass to a vector, and we'll talk about why you would want to do that, what does that do to the vector's direction? So say that we want to calculate the quantity mass times acceleration vector, and we know the acceleration vector is exactly in this direction. When you multiply the mass to that, what direction is the vector that you get? Same direction. Multiplying a vector by a positive number doesn't change the direction. Okay, so that's going to be important. If you multiply a vector by the mass, the direction is unchanged. And now the one that's going to be more complicated to talk about, the second new quantity we have to define is force. And force is a vector. So this is a different thing. Force does have direction. That measures the intensity and the direction of pushing or pulling. And let's say on an object. The units of force are going to be units of mass times length divided by time squared. That's a crazy combination of units. That means that in SI units, the units of force are kilogram meter per second squared. But since force is something we're going to talk about all the time, we're going to rename this combination of units as a Newton. And we'll abbreviate it capital N. So 1 kilogram meter per second squared is 1 Newton. And this is the last thing I'm going to say, and then we'll do the quiz. In this class, there are only 2 ways a force can arise. 2 ways a force occurs. The first one is the weight. That's the force applied to an object by gravity. And the only other way a force can occur is an object is in contact with another object. So contact with another object. Um, okay, well, let's stop there. What we're getting to, so the big equation that we're coming up to, it's going to be, we'll talk about it right at the start on Monday. Um, the most important equation in this whole class is Newton's second law. And that's the one that says F equals ma. But there's a lot of subtlety to using it right. And so, you know, I'll introduce the equation and then we'll talk about how to apply it for a long time. Any questions?